Thanks everyone for dialing into my webinar. Today I'm going to share with you a model-based approach we developed to mitigate the risk of pinnacle precipitation in the telescoped Maira-Borlation-Suzuki coupling process. Here is the outline for this talk. First, I will start with some general discussion on telescoped Maira-Borlation-Suzuki coupling process. Then I will discuss one of the problems we faced during the development of this process, and the problem was basically the precipitation of pinnacle byproduct in our wet cake with the desired product. I will show how we use a combination of distillation model and solubility data to design a process with high yield and no pinnacle precipitation risk. I will also show how we used a combination of phase separation model, distillation model, and pinnacle solubility model to simulate the design space for this process. We still need to concentrate the organic mixture to 6 volume, and we need to still isolate at 0 degrees Celsius. The concentration of the pinnacle in this concentrated mixture would be about 170 milligram per gram. So if we want to keep this pinnacle fully soluble, we need to somehow bring this water level in the organic mixture from about 12% to less than say 5%, and that would help to bring this pinnacle solubility to close to 200 milligram per gram, which would be higher than pinnacle concentration. So it is very important to reduce the water level in the organic mixture to say below 5% to keep pinnacle fully soluble. And this slide summarizes how we achieved that goal. Basically, we found that THF water mixture has isotropic composition about 5%. So we diluted this concentrated organic mixture with fresh THF, about 12 volume of THF, and we brought that water level from about 12% to less than 5%, and we distilled again to back to 6 volume, and that helped to keep the water level below 5%. We could expect in our process with these horizontal lines. So, and this is maximum pinnacle concentration we could expect in our process. So for water weight percentage below critical water weight percentage, pinnacle would be fully soluble in our process. You could also notice that this critical water weight percentage increased with increasing isolation temperature. For example, it increased from 3% to 6% when we increased the isolation temperature active variables. So if we operate at these target values, we need to isolate at above -8 degrees Celsius. Whereas if we operate, say, in this region of the design space, we need to make sure that our isolation temperature is at least greater than 6 degrees Celsius. And we found this design space as easy to visualize and less restrictive and more flexible compared to the one I showed before. In summary, I have shown how we used a combination of phase separation, distillation, and pinnacle solubility model to understand the pinnacle precipitation risk in the telescope Maira-Borlation-Suzuki coupling process, and to design new process with high yield and no pinnacle precipitation risk, and also to simulate the design space. The approach we demonstrated in this study should be applicable to any telescope Maira-Borlation-Suzuki coupling process that use bispin as the Borlation reagent.